Hi, everyone. Thank you all for joining us today. And good evening, good morning, good afternoon, depending on where you are. We've seen that you're connecting from all over the world. So welcome to this webinar about ASME B31, about the design of piping systems. It's going to be presented by Javier Tirenti, who is a senior mechanical engineer with a master's in business administration. He has over 20 years of experience in the design, calculation, and manufacturing of mechanical equipment, such as pressure vessels, heat exchangers, storage tanks, piping systems, and structures in general. He also has extensive experience providing training, both online and in person, and is an ASME authorized. Yeah.
Sorry to interrupt.
No, thank you. And he's also an ASME authorized instructor. So there you can see a bit about his biography. So during this webinar, we're going to discuss the essential aspects that determine the good design of a piping system according to ASME B31. It's going to aim to answer questions such as how is the code organized? How do you select materials for different fluids according to ASME B31? And how do you define the corrosion allowance of a system, and other questions. We do remind you that after this, the webinar will be available here on our YouTube channel if you need to refresh in the future. And at the end of the presentation, we'll have a Q&A session where you can ask your questions. So feel free to start sending your questions through the chat during the presentation so that we can have them ready at the end. You can also email them to us if you'd prefer at info@arvingroup.com. So let's get started. I'm going to pass it over to Javier.
Thank you very much, Autumn, for this very nice, super nice introduction. And thank you, everybody. Thank you for joining us this afternoon, this morning, evening, as Autumn was saying, depending on wherever you are located. It is truly our pleasure to add a little bit of value through these sessions and through our training courses, just to try to make your day-to-day job a little bit easier. So that is the goal of these sessions. As Autumn was indicating before, sorry to interrupt you, Autumn, this is not... Yes, if you can. Okay, now it is working. Yes, thank you so much. Actually, this is not a mistake on our side. We are doing this just for you to see that it's live and that everything is a little bit chaotic at the very beginning. After once you get everything up and running, all is good, but it's just for you to see that we are live. Anyway, thank you so much for joining. And the goal of these sessions, it is just to provide a grain of sand, just to make your day-to-day a little bit easier. And in order to do so, we've found that it is good to carry on and try to answer a lot of questions that we receive during our project and from the different participants that we have in our training sessions. We gather the most frequently asked questions and we answer them, and hopefully that is going to provide good information that is going to shed some light and is going to add value to your day-to-day job. One of the most frequently asked questions that we received is the following: how is the ASME B31 code organized? Well, first of all, we have to remember that there are mainly, and I say mainly because there are many other codes, but there are mainly two codes in order to design piping systems. One of them is the ASME B31, which we are going to be covering today, and the other code is the EN 13480. This code is mainly used in Europe. It is little by little, it is spreading to different countries, the north part of Africa, for example, and some of the countries, Middle East, in some areas, some specific fields. But anyway, that is not the point of this webinar. We are going to be focusing on ASME B31. And if we want to discuss or we want to talk about ASME B31, first we have to cover the structure. So that was the question originally. How is the B31 structure? Well, the ASME B31 is structured in subsections or subcodes, let's say. We have the B31.1 for power piping, B31.3 for process piping, and so on and so forth. Now we are going to, when I change the slide, we are going to cover the most important ones. We have to dedicate a special mention to the ASME B31.12 that we can see at the bottom of the list. B31.12, it is not a new code. It's been around for over a decade now, but with all the projects and all the push that is been given to the hydrogen, especially the green hydrogen industry or projects, it is something worth bearing in mind, because B31.12 is becoming or has become a very important reference in order to develop green hydrogen projects. So it is super important to mention that one, and we can discuss a little bit further at the end of the webinar. Okay, moving on. If we start discussing about the different subcodes or the different committees within ASME B31, we are going to find, for example, B31.1, that is one of the most used codes. This subcode or section within the B31, we are going to use it for the development of electric power plants, for example, or power generation sector. Then we can mention B31.3. This is probably the most subsection within B31. Is the most used subsection. Probably it is very accurate what I'm saying there. It is going to be used for refineries, could be oil, could be paper or textile refineries, also used for petrochemical plants, and it is worth mentioning that it is used only downstream. Then we find another very largely used code, the B31.4. This is for liquid hydrocarbons transportation, only upstream in this case. And in the same way, we find the B31.8 code. It is used for gas transportation. This code is, let's say, the equivalent to B31.4, but for gas transportation. At the same time, it is only applicable for upstream sector. Okay, that is just a brief explanation of the organization of the B31 committee. Now, another question that we receive a lot is the following. Are there any related codes or specifications that complement the ASME B31 code? The answer is yes. And there is not only one, there are a lot of standards, material specifications, and other relevant codes that are used in conjunction with the B31 code. So, first thing in the project is to select the design code that is going to be applicable in the project. Once the subcode, in order to say something, once the subcode or the division B31, 3, 4, 8 or B31.12 is selected, the next step is to choose or to understand which standards are, let's say, permitted, or which standards we have to use in order to select the different components for the design codes that we have selected for the project. So those standards or specifications that are going to define the geometrical characteristics and in some cases the pressure temperature rating of the different components is going to be indicated on each design code. For instance, if we go to the B31.3 code and we are not sure of which components or how to select the different components for a particular design, we go to a specific section of the components, and we are going to find a table, a list of standards that are eligible to be used within that design code. That is the way to be sure of the selection that we have to make. Besides the standard that needs to be used to select a specific component, we need to select the material as well. And the material of the material designation of the different components that are going to be used in a piping system need to be specified as per ASTM specifications. These are the material specifications. So a seamless pipe is going to be A106 grade B, for example, so on and so forth. But this doesn't end here, because besides the standards and the materials, we have some other standards or specifications. In this case, for example, those of the API, the American Petroleum Institute, where we're going to be able to work in conjunction with the ASME B31 design code. So, for instance, for a specific project, we could use a pipe from the API organization that is going to be selected using the API 5L, for example, specification. So that is just one example of how different specifications from other organizations can be used in conjunction with the ASME B31. And apart from that, we can find MSSSP standards or AWS standards as well from the American Welding Society that, of course, are going to be used in conjunction with ASME B31. So this is just a map in order to put on the table all those standards and specifications that need to be controlled, or we need to have them under our radar, because sooner or later we are going to come across one of them, and we need to understand when to use it and how to use them. Here on the screen, I thought about bringing just, let's say, a potpourri of different components that are joined together with the only purpose of providing some aid for us to go and look for the standard that it is going to be applicable in the design of our ASME B31 piping system. So, for instance, if we need to select a pipe or a flange, we are going to go to the right side of the picture, and we are going to see that for a carbon steel pipe, we need to go to the ASME B36.10 standard, or if we need to select a stainless steel pipe, we are going to go to the B36.19 standard. In that way, we identify each component, and then we understand which standard we have to go and check in order to select the component that we are looking for. Good, let's move on. Another question that we get a lot a lot, is how to select materials for different fluids as per ASME B31. This is a very, very good question, and unfortunately in this case I have to bring bad news to you. That is a joke, of course. There is no such thing as bad news. It's just information. Or all that matters is what we do with that information. So the information in this case, it is not going to help us a lot, because codes do not suggest or recommend any specific material for any specific application. So, for example, if we have to select a material for a piping system in order to work with a fluid that, for example, could be dimming water, the ASME B31 code is not going to indicate which material it is going to be adequate to tolerate the corrosion that may be present with that fluid. In this case, is going to be dimming water. So codes, and in this case, it is not just the ASME. It could be the European code or Russian or whatever code. They are not going to indicate which material to use in order to work with this, that, or the other fluid. So if we need to perform a material selection, we were going to have to resort to different sources, such as lessons learned, good practices or best practices. We are going to need to resort to current publications such as API or NACE, or client specifications for those projects where we may have those valuable documents where the customer already knows the process, and the customer already has a specification that is going to let us know where to look and which material to use. At the end, if we do not have the knowledge or the resources in order to select the material, we are going to have to count on a group of metallurgy specialists in order to develop the material selection for the project. Bottom line, design codes are not going to help us in this way. Design codes are only going to list or enumerate the different materials that are available for the whole universe of fluids, but they do not line or they do not specify which material for which fluid. And in order to give you just a brief overview of the different damage mechanisms that we could face in a project, we only need to go and give it a look to the API RP 571. This is a specification from the American Petroleum Institute, and this specification deals specifically with damage mechanisms from, or let's say, for the oil and gas sector. So in this specification, we can see, or this recommended practice, actually, we can see different damage mechanisms as it could be wet H2S, or HCI corrosion, or HIC, hydrogen, high temperature hydrogen corrosion, thermal fatigue, could be temper embrittlement, it could be galvanic corrosion. We could go on and on for a very long time describing and trying to dive into these damage mechanisms, because it is an entire specialization field, which is a very nice one, that is a little bit, let's say, apart from piping design, completely necessary, but it is not the same as piping design. It is just a specific specialization field, which is carried out by metallurgy specialists. Okay, we cannot cover, let's say, material selection as a whole, because we would need probably a master's degree and a program for more than a year, but we can cover another question that is very, very often asked, and it is the following: how to define the corrosion allowance of a system? In other words, what is the meaning of CA 3 millimeters? I am sure that all of you present and following this session are familiar with the term CA 3 millimeters. CA stands for corrosion allowance. So, in basic terms, the corrosion allowance is this part of the thickness of our pipe that is dedicated to withstand the corrosion that is going to happen over the years during the service life of a piping system. That is in basic terms. But why do we often see this CA term with 3 millimeters or 1.5 or even 6? Why 3 or why 6? Well, the answer is pretty straightforward. Corrosion allowance is defined or is obtained multiplying two terms, and one of them is the annual corrosion rate in millimeters by year, multiplied by the service life in years. Let's start by the second one, the service life. Well, the service life of equipment depends on the type of investment, the type of fluids. It depends on many different things. For industrial plants, we could be talking around. We could be talking about a range from 25 to 30 years, more or less. It could be more, it could be less. It all depends on the owner of the project and the owner of the facility. And the service life is around there. And then we have the annual corrosion rate. The annual corrosion rate, it is just the rate per year at which a specific material corrodes with a specific fluid. Obviously, the temperature is kind of important in order to determine this annual corrosion rate. And obviously, we're not talking about a material and a fluid. We are talking about a specific pair, material, fluid. And for example, on the screen, we are seeing a nice graph that was developed by the NACE organization, that is the National Association of Corrosion Engineers. In this case, we are seeing at one graph of the Corrosion Engineers reference book, and in this book we can find many different pairs of materials and fluids, and depending on the temperature and also depending on the composition of the fluid, we're going to be able to determine an estimated annual corrosion rate. And with that annual corrosion rate in millimeters per year or in micro inches per year, if you use imperial units, you multiply it by the service life of the equipment, and you're going to end up with corrosion allowance. Good. Let's move on. Another very important question. What are the main variables involved in the wall thickness calculation of a pipe under internal pressure? Well, this is kind of a basic one, but yet there are still some questions or misinterpretations, let's say, from these equations. All these equations are applicable for thin-walled cylinders. That means that the thickness is very small compared to the diameter. That is the relationship that we can see in all these, let's say that the requirement that we can see in all these equations. And if we explore, for example, the different committees of B31, we could evaluate on the top left corner B31.1, going to the right B31.3, 31.4, or 31.8. We are going to see that the basic reasoning or the basic deduction of these equations, it all comes from the same. It cannot be any different, because they all share the basic principles of classical mechanics. So the principles are all the same for every single design code. And that being said, once that the basics and the classical mechanics principles are used, the different design codes are going to use different safety factors or different factors in order to account for temperature or type of materials or place or site of installation or different details, but basic principles are the same. So we're going to do the following exercise, and we are going to cover ASME B31.3. I could have chosen any other committee or subgroup, but in this case, I'm going to use B31.3 just as an example. So the equation for B31.3 that is stated in section 304.1.2 of the B31.3 code, as I was saying before, for thin-walled cylinders, the thickness of a pipe that is subjected to internal pressure, it is directly proportional to the design pressure that pipe needs to withstand. It is going to be directly proportional to the outside diameter of the pipe as well. So the more pressure we have, the higher the thickness. The larger the diameter, higher the thickness. And then we have some terms that are going to be indirectly proportional, such as the allowance stress, S, that is a mechanical property that is dependent on the material that we select. Then we are going to multiply that allowable stress times the joint efficiency. The joint efficiency of a pipe is referring to the welded joint, and it is referring to the longitudinal welded joint. So if we are using a pipe that is seamless, it has no weld, we can forget about this joint efficiency factor. And the joint efficiency factor is going to be 1 because the pipe is seamless. On the other hand, if we are using a welded pipe with a longitudinal weld, we need to consider the joint efficiency. And this joint efficiency is just the degree of reliability of the welded joint, and that degree of reliability is tabulated depending on the type of pipe that we are using for that particular piping system. Then we have some of the factors, such as factor W, that is dependent on the temperature, and the Y factor, that is a temperature coefficient that is also tabulated, but it is not let's say, as important as the other terms. So, to sum up, the higher the pressure, the higher the thickness required. The higher the diameter of the pipe, the higher the thickness required. The higher the thickness required. The higher, or let's say, the better mechanical properties of a pipe that, or the better the mechanical properties of a material, the lesser thickness that we are going to need, and so on and so forth. Good. Let's move from the ASME B31 internal pressure to the stress and flexibility analysis. What is a flexibility analysis? Well, what is a stress and a flexibility analysis? Well, we need to perform a stress and a flexibility analysis due to the temperature change of a piping system. And what is the temperature change that a piping system might experience? Well, when we erect a piping system or when we install it in the field, normally that piping system is going to install at the temperature at the ambient temperature on the field. Let's say 20 degrees, 25, could be 1 degree below zero, could be whatever temperature that you want. That is let's say that is the ambient temperature at which we erect a piping system. But apart from that, once that the piping is operating, under operation, probably the temperature of the operating temperature of the system is completely different than the ambient temperature. Perhaps that temperature is, I don't know, 250 Celsius degrees, for example. So from 250 Celsius degrees to 25 Celsius degrees, we have a thermal gap of 225 Celsius degrees. We all know what happens to metallic materials when we subject them to a thermal gap. They tend to expand, and that expansion is the cause of a lot of issues and a lot of problems in our plants. So that is the reason why we need to evaluate a system for flexibility and stress in order to define that the system is not overstressed. So on which ways do we have in order to increase the piping flexibility? Well, there are mainly 3 ways to increase the piping flexibility in a system. One of them is by using expansion loops. In other words, to change the direction of the pipe. If we change the direction of the pipe, we are increasing the flexibility, because elbows are a lot more flexible than a straight run of pipe. So when we change the direction 90 degrees, we are the result of that change is a flexible, or at least a more flexible system. Then, we mentioned already the direction change, and by this direction change, we can relocate equipment, for example, if possible, instead of locating item A in line with item B, we can relocate item A, and in order to relocate it, we are going to have to use direction changes. And the third method would be to use expansion joints. These are mechanical devices that are used in order to absorb actual displacements of the pipe. These devices do have some limitations in terms of temperature and pressure, so the preferred method is just to use direction change, not expansion joint. For most applications, it is always difficult to try to generalize and to arrive to a beautiful recipe for every single case, but magic recipes do not work for these designs, since we know that we are normally dealing with one of the kind, or ad hoc solutions. So a magical recipe, it is not going to be suitable for every single scenario. And then we could imagine of a combination of the alternatives mentioned above. This is, in other words, this would mean expansion loops with expansion joint. In some cases, we need to resort to that. A combination of solutions, not very often. Okay, we have arrived to the end of the questions that we had prepared in order to go over this session. So I'm going to move to Autumn to see if there are any questions.
Oh, yes, we have some questions ready and waiting for you. Thank you very much for the presentation.
Okay, my pleasure.
So as Javier said, we are now opening up the question and answer session. We have one question from Fran, who is connected from Buenos Aires.
Okay, good.
He asked, can expansion joints be used with sulfuric acid service according to the code, or any category M fluid in any case? I've seen PNIDs with EJs indicated on such systems, but it feels a bit risky. There's the microphone.
No worries. We are sharing microphones here. Okay, Fran, this is a very, very good question. I have seen it. We have seen it in both ways, used in projects with sulfuric acid and not used in projects with sulfuric acid. In terms of the code, it is permitted as long as the fabricator, the manufacturer of the expansion joint certifies that it is adequate for that fluid. There is no restriction. This is just a matter of the owner or the developer of the project. Normally, project specifications, in our experience, are not going to allow expansion joints in such critical services. But again, this is going to be a matter of the specifications of that specific project. Very good question.
Thank you. We also had another question about which software program can be used to determine the hydraulic and economic system when designing a pipeline network system.
Thank you very much for that question. It is a very good question indeed. This is a little bit outside the ASME B31 code because we are talking about hydraulics or hydraulic calculations here. But anyway, it is a good question. For very simple and straightforward systems, and since everybody has studied fluid mechanics at the university, we tend to make simple calculations with spreadsheets, which are not a bad method if the system is very straightforward and very simple. However, for more elaborated and complicated networks, it is going to be a little bit of a nightmare to try to use a spreadsheet in that case. So there are many solutions, commercial softwares like Pipeflow, that is probably for not overcomplicated networks is probably the best solution. Pipeflow or any other similar software. And the next step from the next step besides those dedicated commercial software for hydraulic calculations would be to go out to a simulation package such as HTRI or any other simulation packages, but probably that is not going to be economical just for a hydraulic calculation. So yes, probably the best answer here is Pipeflow or a similar software.
All right, great. We had another question as well about what are the most used sections within the code.
Very good question, and unfortunately very difficult to answer because that will depend. That will depend on the industrial sector in which you normally operate or in which you participate. If you participate in the whole universe of industrial projects, well, you're going to come across B31 for sure, B33, B31.3, B31.4, 8, and now more and more often B31.12. Which, by the way, we have developed a very nice training session that we recommend that you go and check out. But yes, it depends. It depends on the industrial sector in which you normally are participating.
All right. Unless anyone else has any other questions, I think that might be all for now.
Maybe we can ask the audience if they have any other questions.
I think we got some maybe by email. Oh, yeah, we have another one.
Okay.
Okay.
Good.
Does the thickness calculation change for each of the alternative parts that help with piping flexibility?
Very good question. Thank you so much for that. The answer is yes. The thickness. Well, I am trying to understanding the question as regarding the different components, and depending on the type of components and depending on the morphology of the piping system, the answer is yes. Probably the thickness of the components, most probably or most likely the thickness of the different components, it is going to change due to different considerations or design conditions. If the question is referring to the only the pipe straight runs, and it is referring to providing more thickness to different runs that are subjected to more stresses due to flexibility, no, that is not the case. For the same pipes, independently from the stress that they may be under, the thickness is not going to change. We are going to provide more flexibility to the system, but we are not going to change the thickness of a pipe just due to flexibility. That is the normal rule. That being said, there could be many exceptions depending on the case scenario. And to be honest with you, we are facing more and more challenges in nowadays projects. So there are different tricks that we can apply, but the rule is that no, we do not change the thickness of the pipe due to the flexibility needs. Thank you for the question.
Well, we've got quite a few more actually that just came in, so I hope you're ready for them. Fran wants to know, what are the main differences between B31 and B31J stress intensification factors?
I can see that Fran is very knowledgeable, and Fran really knows his stuff. As you very well know, Fran, the difference is the criteria difference between B31, the old B31 or the current 31, and B31J. It is a whole different approach to stress intensification factors. There are a lot of papers and there is a lot of bibliography that is going to touch on that. Due to time constraints and the purpose of this webinar, we cannot touch on that right now, but the difference is just that the approach is different. It is going to be B31J is going to be more conservative on some cases, less conservative on some others. Some would like to say that it's just a refinement of the old B31. But there is a lot of, let's say, controversy, and there is a lot to be said yet. So thank you so much for the question. If you would like to, to have some more information or more insights, you can always send an email and we can discuss about it. No problem.
All right. We have a couple more questions from the chat.
Sure.
David or David, I'm not sure, asks what about the steps for an ASME certification for piping engineer. I'm not sure if that's...
Good question. Well, there are different steps that are very, very clear. The best thing for you to do is to go to NCEE platform. Right now, off the top of my head, I cannot remember by heart what those letters stand for. But if you go to NCEE, you're going to find the different steps that you need to follow in order to become a professional engineer. I mean, long story short, let me tell you that you are just going to sit for an exam that is from the board in the US or North America, and that is a given that you are going to sit for an exam. But there are some other requirements that you're going to need to provide, your experience in the field, so on and so forth. Best thing is to go to NCEE platform, and there's a beautiful guide there for you to see.
Okay, thanks. And Mauricio had a question about which cases is mandatory reinforcement in branches according to 31.3.
Thank you very much, Mauricio. Very specific question related to branch connections. In which cases is mandatory? Well, the answer is very straightforward. It's going to be it is always mandatory unless you can prove by calculation there is no need for that. I'm just oversimplifying. You just need to go to a specific section of ASME B31 that deals with branch connections, and there is a very nice guide. It is just like a cooking recipe, more or less. You go there and you make some calculations, and you see and you determine whether your branch connection is going to need a reinforcement or not. It is related to the percentage of area that you are removing from the header pipe. So depending on the relationship between the diameter of a branch and the diameter of the header, you're going to need to add a reinforcement or not. It all depends on that calculation. It's just a comparison between areas. So if the diameter of your pipe, of the branch pipe, it is too small compared to the header pipe, most likely is that you're not going to need a reinforcement, an external reinforcement. But if the diameter of the branch is large compared to the header, most likely you're going to need a reinforcement. Now the question is, what is a reinforcement? Because you can reinforce with a disc, with an armor plate, a pad outside the branch, or you can reinforce with a weldolet, or you can reinforce increasing the thickness of the branch or increasing the thickness of the header. So as you can see, it is not as straightforward as one may like, one may want, but yes, it is just a matter of going to the specific section of the B31.3 and check all the requirements. Good question, Mauricio.
Okay, well, I think with that, we're going to wrap things up. Just want to thank everyone for joining us. Thank you, Javier, for the presentation and for answering questions. And we know that just in a webinar, it's not enough time to go into a topic that's so broad and that has so many, so many different branches, and no pun intended there. But if you would like to learn more, we do invite you to check out our course that we have. We have one about this, and as Javier said, we also have a newer one about B3112 as well. We'll send links in the chat, so you can take a look.
Launch the master's degree?
Yes, that's true. We also, in the coming months, we have a brand new master becoming available about the piping, the design of the and the engineering and design of piping systems. So we'll have an ASME certified master that we have you check out, and we'll be announcing its launch very shortly. So we'll send you all those links within the chat, and this video will be available on YouTube so that if you need to refresh or go over something again, you can always come back to it. We do also invite you to follow us on social media and sign up for our newsletters, because that's where we will announce the launch date of the master and let you know about all the things we have going on here at Arving. So we hope that you have a nice rest of your day or evening, depending on where you are. And we hope to see you soon at upcoming courses and events. All right. So thank you very much. Thank you, Javier. And thank you to everyone for joining us today.
Okay. Thank you very much. Bye.
Okay. Take care.
Thank you.